honored to present you Professor Marco Durante. Professor Marco Durante has a Ph.D. in physics. He got it in 1992 at the University Federico II in Naples, Italy, and has dedicated since then his research efforts to the biophysics of high-energy charged particles, with application in cancer therapy and space radiation protection. He is generally recognized, as my colleague already said, as a world authority on the field of particle radiobiology in therapy and space. And he has a patent on proton therapy. He is former chair of the ESA Life Sciences Advisory Group, corresponding member of the ESECRP TG 115 on dose limits in space missions, member of HESHC and former chair of the ESA's topical team on space radiation. He was president of the International Association for Radiation Research from 2011 to 2015. He has been awarded several prizes for his contribution to charged particle biophysics, including the 2004 Galileo Galilei Award in Medical Physics, the 60th Timofeyev-Resovsky Medal by the Russian Academy of Science, and many other awards that I don't list to you now. Maybe the last one, the 2013 Beck and Alexander Award of the European Radiation Research Society. So, it's an honor for me to introduce you Professor Marco Durante, that will speak on the theme FAIR, From Atoms and Planets to Cancer Treatment. Professor Durante, thank you very much for coming and for accepting our invitation. You can speak.
I'm not sure I need the microphone. No, maybe I can speak without microphone, okay? Yes. Is that fine? So thank you for the introduction. I mean, and I have a long CV, which clearly shows that I'm much older than my previous speaker. This is the problem of having a long CV. And today I will mostly talk about FAIR. FAIR means Facility for Anti-Protons and Ion Research, and is under construction here in Darmstadt. So I will try to show you how wonderful is this new tool for research, and also being here in an Italian environment, how many Italians are involved in this effort and how important is the contribution of Italy. So, but before FAIR, I have to talk about GSI, because actually FAIR is constructed on the site of the Gesellschaft für Schwerionenforschung, GSI, which has been founded more than 50 years ago, and for more than 50 years has been a reference center for nuclear physics in Europe and in the world. This is the GSI. Actually, my building is here approximately, and this is the current accelerator, which is 216 meters. We will see that the new one is 1.1 kilometers, so it's quite a different scale. And GSI is very famous, essentially for two things. I mean, the first thing is the new elements. If you look at the periodic table, this is probably, you certainly remember from your chemistry studies, you know, the periodic table, hydrogen, helium, and all the elements. If you go at the end of the periodic table, you see some strange elements like Darmstadtium, like hessium, and so on. All these elements here, you see 1, 2, 3, 4, 5, 6, were actually discovered at GSI. And these other 1, 2, 3, 4, 5, 6 are really with the strong contribution of GSI. And in addition to these elements in the periodic tables, you have many isotopes, many new isotopes already discovered at GSI. You see in red, this is the number of protons, this is the number of neutrons and in black are the stable nuclei, and these red isotopes were all discovered at the GSI. So it's a sort of factory of new elements, where we found new. I mean, it can be a little bit bizarre. I mean, for a person who is not expert in nuclear physics, I say, why? Why you want to discover these elements that do not really exist in nature? And they last a few milliseconds or nanoseconds sometimes, you know. That's because we want to understand the limits of the stability of the nucleus. So how many nucleons we can put together to make a stable nucleus, you know. And so this is something going on and on. The last one here is called Ogenasian, from a Russian scientist, Ogenasian, and that's been discovered in Dubna just very recently. But the second reason why GSI is famous is actually cancer therapy. So completely different topic, you know, we jump to a completely different topic, because this accelerator that was used to produce these new elements was also used to treat cancer patients. This is not a cancer patient, actually, this is just a student, you know, one of that is playing the role of the patient. But 440 patients were treated with carbon ions at GSI between 1997 and 2008. And this was the first trial using these heavy elements in Europe. At the moment in Germany there are 2 clinical centers using this technology, in Heidelberg and in Marburg, one in Italy, in Pavia, and one in Austria, in Medostron. And then there are many other centers in Asia. There is one under construction in US. So that's why GSI was famous. And also the way that the tumors are treated at GSI is completely different. You see, we use a pencil beam scanning. So the beam with the particles is just like a pencil beam that scans the slices of the tumor in the XY axis using a magnet, and then changing the energy, you go in depth. This gives a precision which is absolutely unmatched with other radiotherapy techniques. But now let's talk about the future. This is, let's say, a Google Map 2027. Let's say how it will look like. This is GSI again, and now this is the new area where FAIR will be built. And these are the nations that are members of FAIR. Because, you know, GSI is a GmbH, so it's a German institute. But FAIR is not. FAIR is an international institute, like CERN, just to give you an example. And these countries marked in brown are the partners. You see, Russia, I mean, Russia is big, so it looks like it's all Russia, but Russia is big. But you see India, you see France, you see also partners now are UK and Czech Republic here, Poland. But unfortunately, you don't see Italy. Italy is blue. Italy is blue, which means that there is a lot of Italians working at FAIR, including myself and Walter that you heard before, but we are not really member of FAIR. And that's something I will come back later. So why we are building FAIR? It's not a cheap toy. The price tag at the moment is in the order of 3 billion euro. 3 billion euro. So it's a very expensive toy. Not as expensive as LHC in CERN, but close. Let's say it's really close. Of course, it's a cost sustained by the different countries. But why? The reason essentially is the basic physics. So we want to understand the synthesis of chemical elements in the cosmos. Where are the elements coming from? Why we have so many elements? I mean, we have seen this periodic table. Why? Where are they coming from? How they were formed from the Big Bang until today? The building blocks of life, in particular, that's what we all like. So carbon and oxygen. Carbon and oxygen that are so important for life, where are they coming from? The neutron-star merger, which is something now very popular because of the gravitational wave, we know now that the neutron stars can merge, and you have this burst of gravitational waves. This is another interesting study for FAIR. And finally, the matter in the interior of Earth and large planets, these states of very dense matter. That's something that we can simulate at FAIR. But of course, it's not only pure science, it's also applied science. And several types of application. For example, IT, there is this scientific computing and big data is a very important topic at FAIR. The nuclear clocks, for example, using thorium-229, that's another wonderful application. And of course, something more familiar to me and Walter, space radiation. We heard Walter talking about space radiation already, and yesterday also there was a seminar on this topic. And cancer therapy again, but now cancer therapy, we want to do more. For example, we want to find a way to treat these moving tumors. You see, this is actually a lung cancer. And you see how difficult, if you remember this pencil beam scanning, you can see here how difficult it is to treat a tumor in the lung, which is moving with an extension of something like 10 centimeters. You know, you have to follow the tumor and to destroy the tumor here. Lung cancer is still the main killer among all cancers. And the prognosis is still poor, 20% survival at 5 years. So it's really a big tragedy. And that's what we are trying to do now. But of course, in the last year, that's something I want to say, we were also committed in working on COVID. That can seem bizarre, because you say we are a nuclear physics lab, why we should work on COVID? We did a lot actually on COVID, many activities, you know. Including one activity I want to spend some time now. This was published on the cover of a journal, Radiation Research, recently. You see here the SARS-CoV-2 virus that you are very familiar now, and you see these tracks of heavy ions. We have actually irradiated, you see in the movie here, in this box there is the virus, and this light that you see is the beam hitting the virus. This is a picture, you see, this is the polyester box, and the beam is coming from this direction. Why we want to irradiate the virus with the heavy ions? Well, if you want to make a vaccine, okay, now most of us are vaccinated with mRNA vaccine, but the old style to make vaccine is to inactivate the virus. But if you inactivate the virus by chemicals or by gamma rays, you also damage the spike proteins. If you actually inactivate the virus with heavy ions, you can destroy the RNA with very little damage to the surface. That's the idea. So we can produce an inactivated virus which is almost intact from the external part, which is the only one important for the immune response, because that's what our immune cells will see. And actually, I can tell you, this experiment has been done on June 10, so only a few days ago, but we already had the information from the Helmholtz Zentrum for Infektionsforschung in Braunschweig that actually the virus was inactivated and actually the surface proteins are intact. That's what we wanted. Now we have to see whether the vaccine that will be produced with this new inactivated virus is more effective than the vaccines that we are using now. This is our idea. So I just wanted to show you how science is entangled, you know? It's always it's always a big entanglement. I mean, there are different topics that merge together. For space, this has been discussed already. This is the scientific director of FAIR, an Italian guy, Paolo Giubellino. The technical director is Jörg Blaurock, and the administrative director at that time was Ursula Weyrich. This is when we signed a memorandum of understanding with the European Space Agency, with the DG of ESA that was Jan Werner, who is also from Darmstadt, and this is Thomas Reiter, the astronaut. who has been for many years the point of contact between GSI and FAIR and ESA. So we are officially the ground-based facility to simulate cosmic rays for the European Space Agency. And this is something you have seen already before. There are many interesting things that we can study simulating the cosmic rays on Earth, like the impact on the central nervous system, reducing the uncertainties on cancer risk. And what we are building now, thanks to the funding of ESA, is a full simulator of the cosmic rays. You know, cosmic rays are complicated because there are many, many different particles. But now we are building a simulator of the spectrum of the cosmic rays so that in one shot you can get the same kind of environment that you have in space and you can do the studies on Earth. And then, of course, the biology that we can study with these X-rays. What you see here, I don't know if Walter showed this slide already, probably not. These green spots that you have seen, let's see if I can show you again. These are human cells irradiated with X-rays, and this green spot that you see here are DNA lesions. So the X-rays come and they create damage into the DNA, and what you see here are the DNA repair protein that rush to the sites of DNA damage. They are fluorescent, so you see them in fluorescence. But if you do the same experiment with heavy ions, that's how it looks like. You see the streaks now, because the heavy ions go through the cells and produce the lesions in streaks. And that's what makes the biological effect so different. You see the spatial distribution of the damage. You can see it also here. You see, boom, this is a heavy ion making damage into two cells. Then the damage is repaired. You see that the damage disappears. And this is another one coming. And that's also, you can see this is a zoom now of the cell. This is the nucleus of the cell, and you see the particles creating damage, and then is gradually repaired here. Okay, so this is what we do. We do basic science and we do applied science. And the basic science, of course, is extremely important for the basic knowledge of the universe, but as you see, the applications are very many and in different fields. How is FAIR? I mean, this is how it looks like now. So this is the GSI. This is the accelerator that we have now, where we have done all the experiments that you have seen so far. But then this accelerator will become the injector of this new accelerator, 1.1 kilometers long. Much higher energy, much higher intensity, and this area here will be the area for the new experiments in the future FAIR. The estimates here is that this was actually done in 2019 is the so-called start of phase 0, so using the old accelerator with an upgraded intensity to do experiments that then will be done with the new accelerator at FAIR. Starting date of FAIR 2025, maybe 2026, maybe 2027. I mean, depends. I mean, COVID was not nice. There was, of course, some delay due to COVID, but at that time the estimate was 2025. That's how it will look like. So you see the 1.1 kilometers I told you. Several accelerators, several rings, and that's a movie this movie was shot in June, so that's exactly how it looks like now. You see the ring, this is the ring, these are the trees, the surviving trees. I mean, all the other trees were cut. The ring is now closed. This is for people working at GSI previously. This is probably new because now the tunnel is completely covered, so the accelerator is finished. But you see, there are still these mega crane, these cranes that are working outside for the construction of the buildings on top. This is the southern construction site. This movie is done with a drone. Now with these drones you can really... These are the big cranes. And you see, this is the tunnel of the accelerator. You don't see the accelerator because it's underground now. And there is a continuous movement of trucks going for the construct. This is this is the important part, is the injection. So the old GSI is here, and we inject the particles from here. This is the transfer building. We inject the particles from the old accelerator to the new enormous accelerator. You see again all the trees that were cut has been replanted anyway. This was the agreement with the Hessen state, so there has been no loss, no net loss of trees. So hopefully in a few years it will be completed and will start. It will certainly. This is one of the experiments. So this is called CBM. So this will be the site where a large detector will be installed for the CBM experiment. You see the cave, it's all done in cave, and the walls, this is why it's so expensive. All these walls have to be very thick for radiation protection reasons. Okay, so I think this gives you a very good idea of what's going on in Darmstadt. So, and there will be new movies uploaded on YouTube, so you can follow periodically what's going on. So, of course, one important thing here is the superconducting magnets, because to have this tremendous rigidity that you need to accelerate the heavy ions, you need superconducting magnets, so sophisticated cryotechnology and ultra high vacuum. This is 10 to the 15 times below the Earth's air pressure. 10 to the 15. It's really amazing. And this is to give you an idea of the volumes that you have seen. It's 2 million cubic meters, 600,000 cubic meters of concrete, which means 8 Frankfurt soccer stadiums in terms of concrete, and 65,000 tons of steels, which means 9 Eiffel Towers. It's really gigantic, you see. And in terms of earth to be moved is 5,000 homes. So it's really amazing. And as I told you, the basic activities are structured in 4 research topics. One is this applied physics. Applied physics is not only biophysics, but it's also material research, atomic physics, plasma physics. Then we have CBM. You have seen this K for CBM. This is about nuclear and quark matter. Then you have NuSTAR, which is really nuclear structure and nuclear astrophysics. And finally PANDA, which is about hadron structure and dynamics. So you see there are 3 basic physics topics and one large applied physics collaboration that puts together many different fields. The schedule, you see, is the idea here was still 2025. I got these slides from Paolo Giubellino, from the director. As I said, there could be some delay, and already here was full fair operation 2025 plus, where plus means whatever, and you see these are pretty much the size. Well, but you know, this is normal, you know, even, I mean, very normal for the Italians in the audience. But even for the Germans, there are the examples of the Berlin airport or the Philharmonica in Hamburg, yeah, where, you know, these things can happen, you know. And but this does not compromise the science. You know, this remains the most, from the technological point of view, remains the most advanced tool in the world. Now the Chinese are planning to build something which is very similar to FAIR, and they are fast. So this is a cause of concern. But as yet, I mean, we are still safe. Now I want to say a few words about Italy in FAIR, because I said Italy is not there, even though Italy was among the founding countries of FAIR. And is the first non-member country in terms of industrial return. So normally what happens, the members put money in FAIR, but this money goes back to the members in terms of industry that build material for FAIR. Italy is not a member, but still is getting a lot of money for constructing magnets and other things that I will show. And then of course is the scientific interest. You know, in particular, for sure Italy is very much involved in biophysics. The spokesperson of the Biophysics Collaboration is Vincenzo Patera from the University of Rome, so it's an Italian. And also for his spec, B-spec, which is another experiment, is Benzoni. This is just a list of names, but it's to show that Italians are everywhere in boards and committees, and of course we have the general director of FAIR is Italian. Two department heads are Italians, that is myself, I'm the director of the Biophysics Department, and Silvia Masciocchi, that is the director of ALICE. And then there are many group leaders, including Walter Tingarelli, who is group leader in clinical radiobiology. And many Italians distributed in the Scientific Council, the different PACs, Program Advisory Committees, and so on and so forth. This is a nice picture of the Biophysics Collaboration. Of course, is a pre-COVID picture, as you can immediately realize, but not so much pre-COVID, because it's May 2019, and there are many Italians in this picture. I mean, many Italians. Believe me, this was the Biophysics Collaboration has 250 participants from 27 countries in all 5 continents. We also have a strong collaboration from South Africa, ITEMB. So this is really a large community, you see, where there is a large contribution of INFN, of the National Institute of Nuclear Physics, which is very interested in these applications of nuclear physics. And so I just want to show you, as I told you before, even if Italy is not a member of FAIR, is actually getting money from FAIR, interestingly. Because many companies are working for the construction of pieces of FAIR. For example, the power converter for SIS-18, which is approximately 1 million euro, and 1.8 million for the SIS-100, this is built by OSEM, a company in Bologna. The multiplet magnets, 51 million euro, go to Genova. Genova is one of the most important places in Europe for the construction of magnets. Generally, magnets are always done in Genova. And you see, and they got it. You see, these are these magnets under construction in Genova. And finally, there is the cold testing of the quadrupole modules. This is done in Salerno, in southern Italy. Again, an Italian company involved. So, unique opportunities and challenges, a wonderful endeavor, scientific. I would say also from the educational and human point of view, if you were in these days, you have seen so many young people, I'm probably the oldest speaker, but the other are very young, coming from all over the world. Italy is playing a very important role, and we really hope that Italy will become a member and will be more involved in this fantastic scientific endeavor. Thank you very much.